Swayam Prabha. Digital India. Educated India.
Welcome to module 6, lecture 4. In the last 3 lectures of this module, we looked into mechanical properties of concrete, namely compressive strength and tensile strength. Also, we looked into what are the factors which affect these strengths, particularly compressive strength, and including the test factors. Now, compressive strength is the most important property of concrete, being a material which can withstand more compressive strength as a brittle material. So, can withstand a lot of compressive forces compared to compressive stress compared to tensile or pull tensile stresses. But then other important mechanical properties are elastic modulus, Poisson's ratio, fatigue, abrasion resistance and impact resistance. So, today we will be looking into these important properties, these important properties. So, first we will look into elastic modulus, followed by stress strain behavior, Poisson's ratio, fatigue, impact and abrasion. So, let us look at relevance of stress strain relationship and elastic modulus and Poisson's ratio. Stress strain relationship, sigma is how we denote stress and epsilon. Elastic modulus and Poisson's ratio are needed to calculate deformation, deflection and is necessary to determine also forces sometime in indeterminate structures. So, structural analysis would need this modulus of elasticity particularly, and deflection etcetera are dependent on all this. So, these properties are relevant, and the stress strain curves for materials is important because in structural design they have their relevance. Now, stress strain curves of materials we can classify into 4 types for all materials in general. Of course, we have left out elastomers, but typically these are the 4. So, we will see that concrete is of course nonlinear and inelastic or non-elastic material. Now, simple linear and elastic material, strain versus stress. So, it will follow this stress strain curve during loading, and when you unload it, it comes back to the original with no residual strain remaining. This is nonlinear and elastic. So, an elastic material will come back to its original state when load is withdrawn, but this is not linear, it is non-linear. And if we follow it up further, this is of course linear, but inelastic or non-elastic, it does not come back. So, there is a residual permanent strain, and this is non-linear and non-elastic. So, there is permanent strain, it goes like this, at some level of stress you go, and when you come back it does not close in. So, there is some kind of a hysteresis, and it is non-linear, non-elastic, and concrete belongs to this. So, concrete belongs to this material, concrete, cement paste or similar material, they belong to this. So, it is actually non-linear as well as inelastic. So, when you release load beyond of course certain point, not right in the beginning, at least 1/3 load. If you go on beyond that, there will be some permanent strain when you release the load. Well, since it is non-linear, we have to define the modulus of concrete. Since non-linear, so its behavior is something like this, and then it follows something like this. So, what you do? You define something called initial tangent modulus. Initial tangent modulus, this is what it is. So, the tangent if you draw here, that is we call as initial tangent modulus, but I can draw tangent anywhere, that is called tangent modulus at that particular load. But I can join the origin with this point and I get another modulus, the slope of this line, and that we call a second modulus. And while returning, I can also calculate out the same second modulus from this point, the slope of this line, slope of this line. So, for concrete, modulus can be defined in different way. Initial tangent modulus at any stress or strain level, and second modulus again at any stress or strain level. In fact, we can have a chord modulus joining between 2 points. You can have a chord modulus. So, chord modulus. So, joining between one point and another point. So, that is how we define the elastic modulus for concrete. All right. Now, if you look at stress strain behavior, it is nonlinear, that is what we have shown, and this is attributed to something called creep, that is the deformation under sustained loading. We will come to that sometime. It is one way of looking at it, but there is something more we will look into. We can measure this under static condition, another is under dynamic condition. That means, static condition means you apply the load monotonically in steps and then see how the deformation or strain changes. So, stress at steps and strain at measure corresponding stress, and from stress strain curve you can find out the modulus of elasticity. But you see, from concepts of mechanical wave traveling in solid media, we know the velocity in the media is a function of E. It is a function of E, root E over rho actually. So, velocity is proportional to E over rho. So, therefore, modulus of elasticity has something to do with this velocity, something to do with the mechanical wave or sonic velocities, pulse velocities. So, when wave is traveling through the solid, there is a compression and rarefaction, longitudinal wave traveling through it or any wave traveling through it, there are deformation, and therefore, the modulus of elasticity plays a role, but what kind of modulus of elasticity? That would be bulk modulus. So, you can relate this to anyway, this can relate this to velocity. So, if you have actually obtained velocity in the velocity of wave traveling through this medium, you can actually estimate modulus of elasticity. Now, that is called dynamic modulus. So, dynamic modulus is related to wave propagation within the material itself, right, because velocity of wave propagation or characteristics wave propagation is related to elastic modulus, and one can determine that way. Dynamic modulus, because there is no load applied as such in a big way, and it actually corresponds to initial tangent modulus. So, obviously, this value will be higher than any other modulus, because it is nonlinear. Now, physically, of course, micro cracking of concrete at usual load results in apparently permanent deformation, and that is why it gives rise to nonlinearity. I mean, okay, creep is one issue, but why finally? So, micro cracking of concrete at usual load results in apparently permanent deformation, giving rise to nonlinearity. That means, whenever you are actually, for example, if I have a compressive specimen, applied load like this, Now, if it is sufficient, L by D is sufficiently large, let us say, L by D is sufficiently large, L by D is equals to 2 or something of that kind. So, whenever I am applying load, remember that we said the cracks will form here, there will be cracking, micro cracks will develop because of the tension along this direction. You recall we discussed there will be tension along this direction, and therefore, micro cracks will develop. Now, after a certain period of time, supposing you withdraw the load, this and this results in deformation along this direction too. So, reduction in the length, micro crack will form and there will be reduction in the length. Now, when you release this load, these micro cracks are not going to fill up, they will remain as permanent features in the material, and therefore, it will not go back to its original state. So, once the micro cracks have formed, it will not go to its original state. So, there is some kind of this will actually manifest themselves, these cracks manifest in terms of the deformation, permanent deformation, right. So, therefore, permanent deformation, this permanent deformation, and also this gives rise to non-linearity. So, permanent deformation and non-linearity both comes to this, because suddenly there is an non-linearity means at a given stress suddenly there is an increase, the modulus of stiffness reduces because the cracks has occurred. So, stiffness would reduce and therefore, the material would tend to show lower modulus of elasticity or lower slope. So, material shows a kind of non-linear behavior. To start with, it is like this, to start with it is like this, it goes like this, but then there is suddenly there are a lot of crack formation. So, modulus changes, and this if this continuously this modulus is changing, then it will show a kind of non-linear behavior, and if these cracks do not close, then it will show permanent deformation when it is coming back. When it is coming back, it will show permanent deformation. So, that is the idea, that is the basic explanation to why it shows non-linear behavior. Now, this has been confirmed by tests such as acoustic emission and ultrasonic pulse velocity test, right. So, micro cracking is generally confirmed by this. Now, let us see, let us look at this. So, you see, if I look at, if I apply load like this, if I apply load like this, if I apply load like this on the specimen is here, if I apply load like this, specimen is here, if I apply load like this. Now, this is longitudinal strain, that means strain along this direction, strain along this direction, dimension change. So, strain along this direction, that is longitudinal strain. Then this is transverse strain, that means if I measure the strain along this direction, that is transverse strain, and volumetric strain, because volume changes, original volume, change in volume divided by the original volume. Now, volume actually can be a reduction in the volume change, because this is reduction, this side there is an expansion, and net effect initially there is an expansion, then there could be a reduction in the volume as such. Now, what is acoustic emission? So, this is acoustic emission, we just mentioned about acoustic emission a minute before. We mentioned that you can, when you do acoustic emission and ultrasonic pulse velocity confirms micro cracking. So, what is acoustic emission? We will just quickly look into this for our purpose as much as is required for our purpose. So, what is acoustic emission? You see, if you take let us say a piece of timber or bamboo simply, right, and try to break it, you will find that the sound comes out once it starts cracking, once it starts breaking. Now, this sound is some of the strain energy is converted into acoustic or sound energy, some of the strain energy is converted. So, when you apply strain energy, part of the strain energy is converted into surface energy for creating crack, but part might go as some sort of acoustic energy, because you hear sound. So, when you break a timber piece, you hear sound. So, similarly, a bamboo piece you hear sound, that is basically a kind of when it cracks. So, this crack at the time of cracking there is some sound emission. So, what has been observed here? So, that is actually acoustic emission. In a systematic manner one can actually trace this, find it out. So, emitted sound, as I apply the load, as I increase the load, initially emitted sound is very, very less, and they go on increasing, and the sound starts lot more sound, emitted sound becomes more as the loading progresses. In other words, permanent deformations or non-linearity is related to, all these are related to somewhere lot of cracking, and this is confirmed by ultrasonic pulse velocity also, sonic pulse velocity. Now, what is pulse velocity in a solid material is more compared to cracked material, because velocity of sonic or mechanical waves in solid concrete, very solid concrete, could be of the order of around 4.5 kilometer per second. So, it could be of the order of solid material, it could be of the order of around 4.5 kilometer per second, 4.5 kilometer per second. But in air we know it is around 340 meter per second, 340 meter per second. So, if you have lot of cracking occurring, cracks have occurred, then pulse velocity will reduce. So, pulse velocity starts reducing. Initial reduction is relatively slow, but then it starts reducing as soon as lot of cracks starts appearing. So, therefore, the cracking of concrete is confirmed by this kind of testing, and therefore, if I am trying to plot the stress strain curve, stress as stress increases longitudinal strain, it shows that the nonlinearity of the stress strain curve is largely related to micro cracking of concrete, and so is the case with permanent deformation. Permanent deformation is also related to micro cracking. So, this is the reason why you get nonlinear behavior as well as there is a non closure of the stress strain curve, there is a hysteresis. Now, I mentioned that I can determine it, I can have static modulus of elasticity or dynamic modulus of elasticity. So, we got to do test in two different ways. Static test is done in a monotonic loading, but what we do is we actually initially apply several cycles of loading and unloading at 1/3 of the estimated cylinder strength. We normally test on cylinder, we do test on cylinders. So, central 1/3 is used for metering, this is the portion we use for metering, So, you put gauges actually. In good old days we had actually Lamb's extensometer, it is called Lamb's extensometer, that is what we are using. So, we will put the actually the gauge there, there. So, in the central this will be 300 mm and central 150 mm. So, you put the gauge here, but the deformation is relatively small. So, how do you measure this deformation? It has to be amplified in some manner. It was actually amplified optically during those days, earlier days. Today, of course, you can put in several types of you can put in transducer of the kind of strain gauges, various kind of sensing devices you can put in to measure this deformation. So, several actually deformation measuring devices are there, and one can, or strain gauges could be there to measure this. So, earlier days Lamb's extensometer was used. So, anyway I am not going into the transducer part of it, at the moment it is not necessary, but if you are doing a laboratory test, then you will be using any one of these. This was the old traditional way, and then you measure the deformation there, within the small range. But before doing that, what you do is you crush the cylinder to find out the FCY, cylinder failure strength, and then load it up to 1/3 of FCYL, that is cylinder strength, and then unload it. So, these cycles were repeated to see that at least first of all there is there will be no deformation right in the beginning because of plate settling down and things like that, number one. Number two, this is prior to micro cracking. So, whatever small cracks that occurs should occur, and then after that actually the actual test will be done. So, this will reduce down the effect of creep, some micro cracking would occur, and then hysteresis also will be reduced because of such micro cracking and permanent deformation. So, besides that, there is another important issue why you do it this way. Actually, never the load is never applied one time in a structure. If, for example, if you consider the room you are sitting, and if it is a reinforced concrete slab on which you are sitting, before prior to actually even loading, there will be several loading unloading that would occur actually during construction phase, or even later on several loading and unloading that occurs. So, therefore, determining the stress strain curve after some loading and unloading, that is worthwhile. So, what you do? We actually do about 15 times loading and unloading. The codes, most of the codes would tell you how to do it. So, roughly about 15 times, I think most of the codes would say 15 cycling, 15 times loading and unloading, and then you measure the actual strain versus stress. So, load is then applied monotonically in steps, and corresponding corresponding strains are measured, and it is plotted. It is plotted. Okay. So, in the testing machine, of course, stress cannot be reduced to 0. So, what we do is we find out Chord's modulus. Finally, after this curve is obtained, we find out Chord's modulus as given by this formula, Chord's modulus. So, we find out a Chord's formula. So, F b. So, we actually find out Chord's modulus like this, because this is difficult to reduce it to 0. So, corresponding to 0.5 MPa, this is epsilon, this is sigma, 0.5 MPa, and then so F b. So, corresponding to minimum stress of 0.5 MPa, then up to 1/3 Fc, 1/3 Fc, up to 1/3 Fc, within the kind of severe micro cracking, prior to severe micro cracking. So, F a minus F b, epsilon a minus epsilon b. So, you find out this is your epsilon b, this is epsilon a, and sigma or f or whatever you call it. So, you find out a Chord's modulus according to this, or so the code suggests how much where you have to go to test. So, F c, 1/3 F c is the elastic limit, and often you might find it, often you might find it there itself. All right. So, this is how we determine the static modulus of elasticity. Dynamic modulus of elasticity is determined in this perspective view of the diagram that you see. You have a clamped support which should not exceed 1/20 of the length of the specimen. So, this is length of the specimen, this is length of the specimen, this is L, the length of the specimen, right. This is L, and this should not exceed L by 20. So, it should be less than L by 20. There is a clamp of the support. So, a specimen, rectangular specimen, generally rectangular cross section, you support it, rectangular cross section, actually you clamp it somewhere in between like this, and then you have an exciter. You have an exciter that actually imparts acoustic acoustic pulses or acoustic wave basically there. So, there is a longitudinal wave will be travelling along this direction, they will be travelling along this direction, and here there is a pickup which will pick up the pulse transmission. So, signal that is transmitted through it. So, this is this picks up, and as you go on changing the frequency of the sonic wave that is travelling along this direction, that is exciting this, a time will come at certain frequency there will be resonance occurring, right. There is a resonance occurring. Resonance should be occurring when actually this dimension of this one matches with the wavelength, I mean some sort of matching with the wavelength of the, because the mode would depend upon, because it is a central support, you are trying to vibrate it, and it will be related to length of the, it is related to the frequency, resonance frequency is related to length of the specimen itself. Now, how it is related? It is related like this. Longitudinal vibration is propagated, so you will have vibration along this direction, longitudinal vibration. So, it would be actually exciting in so longitudinal vibration. So, compression and rarefaction they will be travelling along this direction, and from 100 to about 10,000 hertz, at 100 to 10,000 hertz this range you actually make it to propagate, and you will get fundamental resonance frequency when lambda is equals to 2 L. So, when wavelength is equals to 2 L, where L is the length. So, or lambda is equals to L is equals to lambda by 2, at that time resonance would occur. So, you find out the frequency at which resonance is occurring, and you know V is equals to f lambda. So, the frequency you have determined, therefore, lambda is equals to length, lambda is equals to 2 L, lambda is equals to 2 L, and V is actually just I mentioned a few minutes before, V is a function of E by rho, V is function of E by rho. Therefore, you can actually relate E, actually you can relate to V is a function of E by rho and is also equals to f by lambda, and lambda is actually at resonant frequency is known, lambda is given by this equation, L is equals to, since you know L. So, lambda is 2 L, in other words you can find out E, because f is known, L is known, and this is 2 L, L is known, this is 2 L, so you can actually find out as 4 n square L square rho, 4 n square n 4 n square L square rho into 10 to the power 15, where n is the resonant frequency, f that I was saying, n is a resonant frequency. So, you determine resonant frequency. So, resonant frequency, this is lambda by 2. So, therefore, velocity and then velocity is, and then the rho comes into picture, because velocity is under root E by rho. So, if you want to find out the E, it is proportional to V square. So, rho V square. So, E is actually, E will be proportional to, E is proportional to rho V square, all right. So, rho V square, and therefore, you can find out V is given by n lambda, and from that you can find out. So, therefore, knowing the density of the material. So, you have an assumed density or measured density of the material, from that you can find out the modulus of elasticity. So, dynamic modulus can be determined in this manner. To first, what you do is you actually impart longitudinal vibration or mechanical wave, so excite through acoustic waves or ultrasonic, sonic waves from 100 to 10,000 kilohertz, because 10K, 100 to 10K, all right. So, it is actually sound, because sound is from 20 to 20 kilohertz. So, it is not ultrasonic, this is kilohertz. So, this is not ultrasonic, this is actually sonic excitation you can provide, and then find out from this modulus of elasticity. So, this is how we find out the modulus, dynamic modulus of elasticity, and we said that dynamic modulus of elasticity is initial tangent modulus, because no cracks have occurred, nothing has occurred in an uncracked specimen. Is actually we are trying to find out the modulus of elasticity. Usually these values are higher. So, now let us look at modulus of elasticity in terms of what are the factors that affect. So, factors affecting modulus of elasticity. First of all, you see here is your cement paste, this is for cement paste. If you see, this is for cement paste, this is the stress strain curve of cement paste, this is the stress strain curve of aggregate, generally would show something like that, and concrete shows a stress strain behavior of this kind. So, aggregate stress strain behavior is of course fixed, that is fixed by, you have taken the rock and the behavior will be fixed. Cement paste of course is under your control. So, if you improve this cement paste, modulus of elasticity, concrete modulus of elasticity also will increase. So, it depends upon both the paste modulus of elasticity and modulus of elasticity of aggregate. One can think in terms of the range will of course be something like 1 by E of concrete should be equals to proportion of the aggregate, P aggregate, or proportion of the aggregate divided by E of aggregate, plus 1 minus P aggregate, that is your paste, or proportion of paste divided by E of paste, or it might also be written as P aggregate, proportion of aggregate multiplied by E aggregate, plus proportion of paste multiplied by E paste. So, these two will give you actually an extreme boundary of the concrete modulus of elasticity, assuming series and parallel model. I am not going to go to a derivation of this, but this of course, this the range, this boundary, this E c or calculated from this or E c calculated from this, they give you two different values. So, this gives you E c 1, let me call it, this is E c 2. This will actually give you the wide range of the modulus of elasticity, but at the moment it is more important for us to understand the modulus of elasticity of concrete is a function of modulus of elasticity of the paste and modulus of elasticity of the aggregate. So, high modulus aggregate will tend to give you higher modulus elasticity for concrete, and high modulus, obviously paste modulus, if you improve by increasing their strength, then you can actually get higher modulus for concrete as well. So, first thing is this, other factors, wet specimen exhibit higher modulus. Why? Because water has got water E for water is more than E for air, both are fluid by the way. So, wet specimen, the pores are saturated with water. For wet specimen, pores are saturated with water, pores are filled with water. They replace the air. So, therefore, modulus of elasticity is likely to be higher, because now it is the pores are filled up with water instead of air. Modulus of elasticity of aggregate strongly affects the modulus of elasticity of concrete. Higher modulus aggregate exhibiting higher modulus of concrete, volume of fraction of aggregate will also play a role. That is what we have seen for our previous formula. So, I said P aggregate, that is proportion of aggregate, proportion of aggregate, and P paste, let us say paste, which will be equals to 1 minus P aggregate minus voids or whatever there. So, basically proportion will play again a big role, because whichever bounds you take, upper or the lower bound, both cases is a function of those two. The series or parallel model which gives you bounds, both cases it will be related to that. Then mostly E can be related to mod F c, well, compressive strength. Now, E can be related to compressive strength, it can be related to compressive strength. In fact, we have seen that modulus of elasticity governs the strength. Therefore, we can argue it out that strength would be also related to modulus of elasticity. Dynamic modulus is somewhat close to initial tangent modulus, therefore, it is more than E static. And general relationship, empirical relationship people have found out for modulus of elasticity is E is a function of k into cube compressive strength to the power n. And IS 456 2000 for design uses this F c as F c k characteristic strength and n as 0.5. So, E is written, can be written as 5000 under root F c k. It is meant for design. So, this is actually a conservative value. In fact, it will be something like this. If I I'll just plot it here. Before this, I'll just plot it here. It will be something like this. If I plot F c concrete cube strength and E, then or under root F c, then you get all sorts of scattered results, and you can plot a curve. So, this is what it is trying to do, linear curve, or some people put it as some m c to the power n, maybe 0.6 or whatever values are, and one can, because this scatters are there. Now, code would use a value of modulus of elasticity, the code the actual values will be there, and the relationship that code tends to use is somewhere there, conservative value of E, it takes lower value of E, because effects of creep, long term behavior, several other things comes into picture. So, code takes this sort of stand actually. Actual values could differ. Now, since this is under root f c, I said it can be f c to the power something else. So, different codes may use different one, but IS 456 of course uses E is equals to 5000 under root f c k. So, the line is somewhere, the slope is 5000 and under root f c k, that is what it uses somewhere down there, because it takes long time behavior and other things into account, and therefore, try to use a conservative value. So, that is it, that is related to what code uses, and it can be related to compressive strain. Now, let's look into now stress strain curve. If you look at stress strain curve at a constant strain rate, now last class or last lecture, if you remember, we talked of constant rate of loading. Now, you can do test by constant loading, rate of loading, that means you apply load at a particular pace, 14 MPa per second, right. So, you apply load at a constant rate, and we have seen rate of loading actually changes the behavior, the like behavior changes. So, supposing I apply, now I can apply in terms of strain at certain micro strain per second, some strain rate. So, if I apply load at fixed strain rate, and I told you also that it is difficult to apply this, you need a machine which is capable of applying the servo controlled, it is should be capable of applying the maintaining the strain rate at a fixed rate whenever required, and that would require a controller and a servo control system and so on and so forth. So, if you are applying load at a constant rate, you will find that depending upon normal weight normal weight concrete behaves in this manner, while lightweight concrete shows this kind of behavior, because you are able to now, since strain rate is there. So, this portion of the curves becomes available, and this behavior is similar in compression as well as in flexure, and compression behavior in flexure. So, you find some sort of behavior like this, where this is the E max, or rather F max or sigma max, maximum stress, and corresponding to this we call as epsilon 0, that is the strain at maximum stress, strain at maximum. For lightweight, this would be the maximum stress sigma max, and epsilon 0 would be this much. So, epsilon 0 and sigma max, these are the two ones, and you see this kind of a behavior. So, people have tried to fit it approximate equations to this, empirical equations to this, and this empirical equations that have representing this, the simplest, there are maybe many more complex relationship, but one of the simplest relationship is of this form, where E is the initial tangent modulus, and which is twice sigma max divided by epsilon 0, and sigma is the stress at any point, epsilon is the strain at any point, epsilon 0 is the strain at maximum stress. So, epsilon 0 is strain at the maximum stress. So, this sort of formulae is available through which you can define the stress strain curve, and there are complex formulae also available. So, this was stress strain curve of concrete. Now, we actually, if you just before I go to this, in flexural design, therefore, one should be using this sort of curve in compression. So, this is, if you remember flexural design, flexural stress strain curve given in the code, stress strain curve given in the code would be something like this. Stress strain curve of concrete, if you recollect, this is strain in flexure. If it is a beam, section of a beam, if I am looking at a section of a beam, this is the steel reinforcement, this is the concrete. Anyway, so stress strain curve will be like this, stress versus strain curve. If you have seen idealized stress strain curve, it will be 0.002 here and 0.0035 stress strain curve, and this is actually okay, FC or whatever you call it, the stress, maximum failure stress. Now, this is an idealized stress strain curve, idealized stress strain curve, of concrete. In fact, stress strain curve of concrete should look like something of this kind. Some stress strain curve of concrete will look like, let me draw it with red color. Stress strain curve of concrete will look like this. all right, maximum stress and here. Now, this is idealized stress strain curve, beyond that you assume is as if it is straight line. So, actual stress strain curve of concrete is like this, and this is important in flexural design. So, the measured stress strain curve that we have seen, measured stress strain curve, actual stress strain curve observed as we have seen, this is idealized into this sort of a straight line curve, and of course, certain factors are applied to bring down the load as well, that I am not discussing at the moment. So, this importance of the stress strain curve is here, because in flexural design you got to use this. So, idealized curve is something of this kind. This is arrived from this real behavior. This is arrived from this real behavior. So, that is the importance of the stress strain curve. Now, let us look at next property, which is Poisson's ratio. This is important to find out lateral deformation when you have applied a longitudinal stress, right, in axial situation and so on. So, therefore, if you apply load, when you apply load, you can see this is compressive loading, this is tensile, the strains are here, and this is compressive stress. So, what happens is, this is a longitudinal strain, this is the volumetric strain, that is what we talked about earlier, that when we talked of ultrasound pulse velocity and acoustic emission, and this is the lateral strain, which is in the opposite direction, it is in the tensile direction. So, mu is defined as lateral by longitudinal strain. So, this is lateral by longitudinal strain, mu is defined by this actually. So, from this if you try to calculate out the mean, ratio of, for example, this divided by this ratio, this divided by this ratio, all right, or let us say at 400 strain of longitudinal strain, corresponding to this is maybe whatever the value is, and similarly so you can actually find out the mu values. Now, mu values if we calculate out in this manner and then plot, we will see that it is roughly around 0.2, it is roughly around 0.2 up to about 70% of the load for two different concrete. Good old days, people conducted experiments and found out. But beyond that point, actually it starts increasing. It starts increasing, can go close to about 0.3, 0.4 or so on and so forth, with the like if your stress to strength ratio. So, when before failure, Poisson's ratio increases, and we understand this because a lot of micro cracking would have occurred, and that would have caused lateral strain to expand, increase at a faster rate than the longitudinal strain, and this is manifested here also. This is manifested in this diagram also. Suddenly, there is a lateral strain increasing, not here it was increasing in slow manner, but it was started increasing in a faster manner. While this is increases, although there is a faster increase here, I mean this is not really it is almost close to linear sort of situation, slight variations are there, but this increases at a very fast rate, this increases at a fast rate, but this increases still at a faster rate, and this we can understand from the physical scenario, because micro cracking in the would result in lot of transverse deformation. Longitudinal deformation also would be there, but lateral deformation will increase significantly because of the micro cracking. So, beyond 70% of the load, actually your Poisson's ratio increases significantly, and up to its constant, almost constant up to 70% of the strength, 70% of the strength, 70% of the strength. Generally, it varies in the range of 0.15 to 0.20, that is what is determined from static modulus test, but you can determine dynamically Poisson's ratio also from ultrasonic pulse velocity test, from fundamental or sonic velocity test from fundamental resonant frequency of longitudinal vibration of concrete beam. Similar test that we did for modulus of elasticity. Now, how do you determine this? How do you determine this actually? Because the bulk modulus, it was related to bulk modulus. So, this is the relationship between, this is involved in the velocity equation. The Young's modulus is related to the bulk modulus in this manner, where mu is the Poisson's ratio. So, velocity, frequency, length, and it is related to modulus of Poisson's ratio is related to that. So, this is the velocity, pulse velocity, resonant frequency, beam length, and Poisson's ratio. From that one can find out. So, from dynamic testing also you can find out Poisson's ratio. and generally dynamic modulus again gives you higher value of Poisson's ratio, because higher value of Poisson's ratio usually 0.2 to 0.24, and higher the strength of concrete, Poisson's ratio is lower. Higher the strength of concrete, Poisson's ratio is lower. So, that is related to Poisson's ratio. Now, let us look at another mechanical property is called fatigue. Fatigue is related to reversal of stresses, and you can understand the importance of this one in many structures. The load that is applied in most of the structure, the imposed load, that is actually quasi static, but that we do not call it fatigue. Like, because even in a building where you are sitting, let us say right now, if it is on the first floor or in the higher floor other than ground floor, the slab that you are actually sitting on or your chairs are, the load you are coming and then you are going out. So, there is a kind of stresses, it is quasi static actually. What happens is, by and large we assume that to be static, because major load will come from the permanent fixtures such as furnitures and things like that, the imposed load, human contribution will be relatively less. So, we assume it to be practically static. So, fatigue is not there, but supposing it is a bridge, or assume a structure in marine environment where waves comes and hits here, waves comes and hits, waves comes and hits. So, it is actually under kind of a reversal of stresses would be occurring. Bridges, this vehicular load comes in, vehicular load comes onto the vehicular load comes onto a bridge deck, and then it moves, bridge deck, and then it moves. So, therefore, there is a reversal of stresses there, reversal of stresses onto the deck. So, therefore, this reversal of stresses is related to what is called fatigue strength. Reversal of stress is related to fatigue strength. Okay. So, let us see, and in fact, the load any structure or any structural element can carry under reversal of stress is much lower than the load it can carry in static conditions. So, fatigue is related to repeated loading. Under repeated loading, materials fail at load lower than static strength. The failure load being lower with number of repetition, and it is a fatigue failure. A simple example is given. Supposing I have a wire, small wire, and I try to pull it, I can never break it. Binding wire, which are used for binding the steel in concrete, coil casting concrete. But if I try to bend it in this manner, that means bend it in this manner, reverses the stress. There is a reversal of stresses. So, first you bend it in this manner, then bend in the reverse direction. So, first you bend in this manner, then reverse direction, you go on doing this, after some time it will break. So, repeated loading you can it fails at much lower load, and that is basically much lower load, and that is basically a fatigue failure. Therefore, fatigue failure occurs at much lower load. So, the mechanism that is what is that is what we define as fatigue, and let us see what happens in case of concrete. Now, steel has an interesting behavior. We define something called endurance limit. What happens is, as you go on number of repetition, if you apply a load, say load which is 50% of the strength, and then reverse the stresses, maybe bring it to 0, some reversal, bring it to 0, take it to near 100%. Number of I mean, one thing, the amplitude or the maximum stress, positive and the negative, or maximum reversal range of the stress range in which it is reversing, let us say we keep it fixed. Now, after a certain period of time you will find that it fails. Now, if you lower the load, if you lower the range in which you are operating, then it will take more number of cycles. So, the number of cycles is a function of level of the stress, reversal where you are reversal of the stress is occurring. Now, endurance limit is defined in this manner. It is much better to define this and come back to this. If you look at this diagram, on this axis number of cycles drawn in log scale, because 10 to the power 2 etcetera, this is in log scale, and ratio of the fatigue strength to short term static strength, fatigue strength to short term static strength. So, actually if you are operating at fatigue strength, you will find that in case of steel, this is mild steel, in tension you do reversal of stresses, but beyond 10 to the power 7 cycle or some such cycles, slightly above 10 to the power 6 cycles and 7 cycles, the endurance, the fatigue, the load at which reversal, this is occurring at 0.4 or so, 0.4 or so, close to 0.4. So, close to 0.4. So, around like 250 MPa is a yield strength of mild steel. If endurance limit is around 100 MPa, close to 100 MPa. So, that means if you apply less than 100 MPa and do stress reversal, actually it is not going to fail. Now, endurance limit is defined, therefore, endurance limit is defined as fixed endurance limit, that is repetition beyond which the fatigue strength remains constant. So, what is fatigue strength? Fatigue strength is the number of repetition or the strength which it can withstand at certain number of repetition. So, it is related to both repetition and the level of the strength. Now, endurance limit is that level of the strength beyond which, actually lower than that strength, it can withstand a large number of repetitions, because fatigue strength becomes almost constant. Now, concrete does not have a fixed endurance limit, concrete does not have any fixed endurance limit, concrete does not have any fixed endurance limit. In tension, concrete in tension, it shows continuously, if you the fatigue strength will go on reducing as you increase the number of cycles. So, here also concrete in compression, same thing. So, therefore, how do I define this strength? There is no endurance limit. How do I define this endurance limit? So, there's steel is advantageous in that sense from usefulness point of view. I mean, what I say, a design calculation point of view or understanding point of view, because you have got a fixed endurance limit. So, therefore, if you know it is likely to come under cyclic load, you assume that it can withstand around that endurance limit is a is which will be the which you can use in design. In case of concrete, you can't do that, because it will go on reducing. So, what we do is we take the fatigue strength corresponding to 10 to the power 6 cycles as the fatigue compressive strength. Similarly, in this case 10 to the power 6 tensile fatigue tensile strength. So, fatigue compressive strength and tensile strengths are defined with respect to 10 to the power 6 cycles, because it will go on reducing. For steel, of course, you can use the endurance limit. So, it will go on reducing with number of cycles, increased number of cycles. All right. So, this is how we define. Now, in concrete, two types of fatigue failure is distinguished. The one, you see, sustained load near the static strength under increasing load causes failure. So, it is static fatigue or creep rupture. Now, concrete shows creep at ordinary temperature. That means, if you put a load, we will discuss this in subsequent module. That means, if you keep the load constant and over the time period, over the period of time, you will find the deformation is increasing, and it can have a failure also depending upon the situation. So, under sustained load, concrete exhibits kind of deformation, and that is related to phenomena of creep. So, if you have sustained load near the static strength, now fatigue is also nearly sustained, because you are reversing the stresses and near the static strength. So, you increase the load and it causes the failure, and this is related to static fatigue or creep rupture. So, if you are reversing the stresses close to the static strength, then there failure can be by creep rupture, because sustained load is sustained, very static load is sustained, plus minus something is always occurring, plus minus something is occurring. So, this sustained load can result in creep rupture, because load is sustained very close to the static strength. Repeated siding loading is of course other case, where you are operating at much lower level, but then it fails because repeatedly you have done reversal of stresses are being done over a large number of cycles. So, these are the two situations, and we can see the behavior in this manner. If you look at this diagram, usually in this case what you are doing, you are sustaining the load for 50 days. 3 minutes stress strain, rapid loading stress strain curve is like this. This axis is strain, this is stress. Rapid loading stress strain curve is like this, and here it might fail. If you finish it within 3 minutes, it will show you failure like this. I do not have a, here I am only controlling the rate of loading in terms of load per unit time, not in terms of strain controlled situation. So, what will happen? Very rapid loading, the micro cracks would not form, but suddenly there will be a sudden brittle failure at some higher load. So, it fails somewhere there. But if you are loading under, let us say, 3 minute failure, up to failure, which could be the case in case of static monotonic loading. So, it will fail somewhere there, not much deformation or such thing, it will not show. It will show this if you have a strain controlled situation. So, a kind of what we call strain softening would occur. As the strain increases, strength it can load it can carry is lower. So, if you go on increasing, this is normal stress strain diagram, but if it is 3 days, this is about 3 days you take. If you 3 days if you take, then you find that keep the load for 3 days. So, at 80% of the static load, it will actually 80% of the static load it will fail. Keep the load for 3 days, it might fail somewhere 80%. I mean, this is a notional thing, one cannot take it for all the time granted, the values might differ from test to test. And if you keep it for 50 days, it is actually fail at somewhere there. So, depending upon this 20 minutes, 3 minutes, 2 days, 3 days and 50 days. So, increasing the test duration, then which means that my rate of loading I am decreasing, and at lower rate of loading we have seen that it fails earlier. So, 50 days same load you are applying in 50 days, you find that the load carrying capacity is much less. So, I can actually have a kind of a envelope, right. So, you can call it static fatigue failure envelope, because this is related to micro cracking or creep behavior and so on. So, very close to the load, quickly if you load it, it fails at higher load. You take it for a longer period of time, it will actually fail after certain period of time, because it is sustained for 50 days. So, it will actually fail. So, this is related to static fatigue failure. So, close to this one, if you take if you do reversal for 50 days, it will fail. So, if you do reversal somewhere here, if you do a lot of reversal, the time frame it will be related to this. Actually, failure would occur even though you have not gone to too much of a cycle. For example, for 0 cycle, this situation is for 0 cycle. So, even if you have not got too much of cycle, it will still fail. So, this is actually related to static failure, static fatigue failure, So, or creep rupture as we are calling it, creep rupture, right. And this is again strain versus stress curve. So, limit of strain after approximately 30 years. So, if I look at it, static rupture curve is here, maximum strain after 30 years, this envelope gives you 50 days we looked into. So, 0.6 of the strength, 60% of the strength, if you load it to after 30 years, deformation will be somewhere here, after 30 years deformation will be somewhere here. Of course, it will not fail, but if you put it at 80% after 30 years, it will actually fail. After 30 years actually it will fail. So, this is it, and this is the usual short term strength, which is about 3 minutes or so. So, 0.3, so let us say 30% of the strength, it will actually after 30 years deformation will increase, but it will still not fail. So, it fails up to something like 80% of the static strength over 30 after 30 years, and so, but if you have something more than that, it will fail. So, this is how this is related to this fatigue, and if you do reversal of stresses, one cycle the behavior is like this, 3000 and first. So, that this hysteresis area reduces significantly, and then this area would increase. So, what we will do is the fatigue, we have introduction to fatigue I have given to you right now, and you can see that after a long period of time, because after long cycling, number of cycling causes more micro cracks to appear. So, therefore, this increases. In the beginning there is a reduction, but under long cycling actually more micro cracks form under fatigue loading, because there will be frictional and heat generation as it happens, or whatever mechanisms are there. So, fatigue causes failure in this manner. We have something called modified Goodman's diagram. Here this diagram helps us in finding out what is the stress level or reversal of stress a concrete can withstand. For example, this curve, this is a minimum compressive stress line, this is a minimum tensile stress line. Now, uniaxial compression, if you are operating at 40% of the strength level, or let us say 20%, 10% of the stress level, you can do reversal up to this and come back in compression mode only. So, failure would occur at 10 to the power 6 cycles, and if you are applying, let us say, tensile stresses, you can go up to 20% of the tensile strength, 30% of the tensile strength, and reversal can occur from 10% of the compression to 30% of the tensile. If this is in compression, uniaxial tension and compression, this is in flexure, and if you are doing purely tensile, so at 10% of the tensile load, you can go up to this and come back. So, modified Goodman's diagram can be used to find out what level of stress reversal you can do, what level of stress reversal you can do, right, at what level of static strength, static stress level. So, at 10% of the stress level, you can reverse the stresses given from this diagram. Say if it is compressive stress, if it is tensile stress, one can determine from this diagram. So, modified Goodman's diagram can be used to find out what level of stress, range of stress you can use. Impact strength is again can be related to compressive strength, and it depends strongly upon aggregate type. Lower for lower water stored concrete, and lower MSA improves impact strength, and that is shown by this diagram, different types of aggregate. This is the number of actually impacts actually it can take, the way it is measured depending upon compressive strength. So, both impact strength as well as abrasion, they are function of compressive strength, and impact is loading at a very high load, high rate, very fast rate. So, rate of loading is very high, impact is related to that. Abrasion is again related to compressive strength, as you are rubbing, how much, what kind of it depends upon different types of test. Actually, you can rub it and find out percentage of the material generated, and this is also related to compressive strength. So, bond to reinforcement again for plain bars and deformed bars related to compressive strength. So, bond strength, so bond by pull out test one can find out. So, what we find is all these strengths are related to compressive strength, bond, fatigue, bond, impact and abrasion resistance, these are all related to compressive strength. Essentially, higher the compressive strength of concrete, all other properties can be related to that, and they improve. So, higher strength means better impact resistance, better abrasion, and better better abrasion, better impact resistance or impact strength. So, all properties actually higher modulus of elasticity. So, I think we have discussed in this one elastic modulus, Poisson's ratio, and fatigue and impact. With this module we complete. Thank you very much, and next 7th module we will look into creep and shrinkage. Thanks.